Okay, let's unpack this. If you were listening to our last deep dive, we started something big. We opened a loop.
We did.
We took this massive, often confusing concept of how quantum mechanics becomes the real world. The chair you're sitting in, the coffee you're drinking, the ground beneath your feet. And we looked at it through a very specific, very mechanical lens.
We did. We spent that entire session unpacking the work of Levny Moten, PhD, specifically his paper on quantum condensation.
Right. And today, we are back for the second half of that loop. We are diving into the follow-up paper, Quantum Un-Condensing QUC. So, welcome back. If you're just joining us for the first time, or if you just stumbled onto this stream, think of this as part 2. We aren't introducing a brand new topic.
No, not at all.
We are completing the picture we started painting last time.
Exactly. And just to set the tone here, because I think this is important, this isn't a debate. We aren't here to argue about the multiverse or consciousness or, the philosophical implications of free will.
No, this is much more grounded.
It is. This is a conceptual narrative. We are exploring a specific framework that Moten has built to make sense of the quantum world without needing magic. It's calm, it's reflective, and honestly, it's physically fascinating.
So let's quickly recap where we left off, just to make sure we're all standing on the same foundation. Because without that foundation, today's discussion is going to sound like nonsense.
It absolutely would.
In the last deep dive, we talked about 2 main characters in our story, the vapor and the droplet.
That was the core analogy. We established that a quantum state, before it's measured, before it becomes a thing, is like vapor.
Okay.
It's diffuse, it's spread out, it's coherent. It holds all these possibilities at once, just like water vapor fills a room without settling in one specific spot. It's not here or there. It's kind of everywhere.
That's the superposition part.
Yeah.
The all possibilities at once.
Exactly. That's the vapor. And then you have the condensation.
And this is the moment reality happens. This is the event. The vapor touches a cold surface, which represents the environment, and boom.
A phase change.
It undergoes a phase change. It stops being a cloud of possibility and becomes a single localized droplet.
Precisely. And the key takeaway from that first discussion, the thing you really need to hold on to for today, is why that happens. It's not magic.
Right. It's about the record.
It happens because the environment creates a record. The droplet is stable because the surface knows it's there. The air molecules bounce off it. Light hits it. The universe has taken a note. That is what makes reality real. Reality is just a collection of records.
The droplet is the fact. It's the classical world we live in. It's the car keys I can't find, but which are definitely in one specific place.
Yes.
But here's where it gets really interesting, and this is the launch pad for today's deep dive. In the real world, in nature, droplets don't stay droplets forever.
No, they don't. That's the nature of water.
If you heat them up, they evaporate. They turn back into vapor. So the intuitive question, the one Moten asks right at the beginning of this new paper is, can we do that with reality?
That is the central question. Can the droplet evaporate?
Once a quantum system has condensed into a hard fact, once it's a droplet on the glass, can we turn it back?
Can we?
Can we take a definite reality and melt it back into a probability?
It sounds like science fiction or maybe time travel, but Moten argues that physics doesn't actually forbid it.
Is it possible?
The thesis here is that, yes, quantum uncondensation is possible. We can turn the droplet back into vapor, but, and this is a massive but, it is deeply, deeply constrained.
And that's the theme we're going to explore today, asymmetry.
Yes.
The loop exists. You can go from vapor to droplet and back to vapor, but it doesn't spin freely. Condensing is easy. Nature does it for free.
It's the default path.
Uncondensing, that is hard. That requires engineering.
It requires fighting the flow of the universe.
So let's get into section 1. What does uncondensation actually mean? Because when I first read the title, I just imagined making things blurry again. Like if I have a sharp photo and I shake it, it gets blurry. Is that what we're talking about?
That's a great question, and it's a very common misconception. People think quantum just means fuzzy or random.
Right.
But uncondensation isn't just about losing focus or scrambling a system. It's much more precise than that. Remember, the definition of the droplet, the classical fact, is that it has a record.
Right. The environment knows it's there. The surface tension holds it. The information exists.
So to turn it back into vapor, to turn it back into a coherent quantum wave, you have to undo that record.
You have to erase the information.
Completely. Think about the analogy. If you have a droplet on a cold glass pane, what keeps it there? The temperature difference, the surface tension, the interactions with the molecules of the glass.
All those tiny records.
Exactly. To turn it back to vapor, you have to apply energy to disperse those molecules back into a cloud. But in the quantum world, dispersing means you have to prove to the universe that it doesn't know where the particle is anymore.
Okay, this is heavy. So it's not enough to just scramble the system.
Yeah.
I have to fundamentally erase the witch path information. I have to delete the file.
You have to delete the file, and you have to delete any backups the universe made. If the world knows where the particle is, it cannot act like a wave.
It'd have to act like a particle.
It acts like a particle, a droplet. To uncondense, you must restore the condition where no accessible record exists that distinguishes between outcomes.
So if I measured a particle and said it is at point A, and I wrote that down in a notebook.
Then you have to erase your notebook.
Okay.
And you have to erase your memory of writing it. And the air molecules that bounced off your pencil while you were writing, and the photons that reflected off the page into your eyes.
Wow. Okay. This sets up the difficulty immediately. Irreversibility. The reason we can't just walk through walls or undo the past isn't because of some fundamental law that says stop.
No, it's not a hard rule like that.
It's a problem of information.
Exactly. It's a problem of lost access. Moten puts it really well. Irreversibility isn't a fundamental prohibition. It's just that the information about the outcome has escaped into places we can no longer reach to erase it.
It's like a cosmic needle in a haystack.
Infinitely worse than that. It's a single molecule of steam in the entire atmosphere of the planet. Good luck finding it.
This leads us perfectly into the structure in the paper.
Yeah.
Moten breaks us down into 3 regimes. He classifies how hard it is to uncondense something based on something he calls the record radius.
The record radius. It's a brilliant concept.
It sounds intuitive.
It is. It's simply asking, how far has the information spread? In our steam analogy, it's the volume of air that contains the steam. If the steam is in a tiny jar, that's a small radius.
You can control that.
Right. But if the steam has blown away across the entire city, that's a huge radius.
It's a measure of containment.
Exactly. And the difficulty of reversing the process scales with that radius.
Okay, so let's walk through these 3 regimes, the possible, the hard, and the effectively impossible. Let's start with regime 1, the possible.
This is the scenario where the droplet is tiny. The record radius is microscopic.
Give me the visual.
Okay, imagine you're breathing on a cold window in winter. You see a tiny bead of fog start to form. A droplet is just beginning to nucleate.
They could do that.
But before it can settle and become a heavy, dripping drop, you immediately blow hot air on it. What happens?
It vanishes. Instantly. It goes right back into the air.
Exactly. It uncondenses instantly. Why? Because the interaction was brief. The record of that droplet hadn't spread very far. It was right there on the surface, and you intervened. You still had complete control over the immediate environment.
So in physics terms, what is this? What does this look like in a lab?
These are things like interrupted measurements, or situations where we control the entire environment with incredible precision. Have you heard of the quantum eraser thought experiment?
I have, but let's avoid the technical jargon. How does it fit here?
Well, think of it this way. If you set up an experiment where you could know which path a particle took through a maze, that's the droplet forming.
The information is there, waiting to be read.
Right. And because that information exists, the system starts to act like a particle. It commits to a path. But if you then do something clever, you scramble that information before looking at it so that even you don't know which path it took.
You erase the potential record.
Yes. And because you erase the record, the condensation reverses. The vapor returns. The particle starts acting like a wave again, as if it took all paths at once.
That feels like cheating. It feels like you're tricking the universe.
It's not cheating, it's just very careful accounting. You're ensuring no permanent record is ever made. We see this in labs all the time with something called reversible dephasing.
That's that.
Imagine a group of runners starting a race. They all start at the same line, perfectly in sync. That's our coherent quantum state.
The vapor.
Exactly. Then the gun goes off and they all start running at slightly different speeds. They spread out, they lose their coherence. It looks like the signal is lost, like the vapor has dispersed.
The droplet is forming. It's decohering.
But because we're in a controlled lab, we know exactly how fast each one is running. We can fire a second gun, a special pulse, that tells them all to turn around and run back towards the start line at the same speed they were running away.
And they would all arrive back at the same time.
perfectly in sync. The signal is restored, we've refocused the vapor, we've gathered the steam.
We can gather the steam because we still know where it is. We control the room. We kept a ledger of how fast everyone was running.
We never lost the information. The record radius was contained within our experimental setup.
So uncondensation is real. It's not theoretical. We do it.
We do it, but only when the record radius is very, very small. We are talking about microscopic systems in highly controlled, very cold, very isolated environments.
We're catching the droplet before it really settles.
Exactly. We are intervening before the cement dries, before the universe has a chance to make a permanent copy.
Which brings us to regime 2, the hard.
The hard regime. This is where things get tricky, and that asymmetry starts to bite.
The scenario here is that a real measurement happened, a record exists, but the system is inside a sealed box.
Right. The droplet isn't just starting to form, it has fully formed. It's a real drop of water, but it is trapped inside a perfectly sealed small container.
Okay.
To turn it back to vapor, you can't just wish it away. You can't just blow on it. You have to carefully manipulate the pressure and temperature inside that specific box.
It takes work, real physical work.
It takes significant work. In physics, this is the entire world of quantum computing and quantum error correction.
How so? Connect those dots for me.
Well, imagine you have a quantum bit of qubit. It's in a beautiful state of superposition holding a 0 and a 1. That's our vapor.
Got it.
But then a stray microwave photon or a tiny vibration from the outside world bumps into it. That's a measurement. That's condensation. The qubit starts to leak its information into that photon. It's starting to become real and lose its quantum magic.
The droplet is forming. It's collapsing into either a 0 or a 1.
Exactly. But if we have built the system with what's called redundancy, if the information of that one logical qubit is distributed across a few other physical qubits that we control, we can sometimes perform an operation to rewind that interaction.
We can catch the error and reverse it.
We can. We can detect that an error, a small condensation event has occurred, and we can apply a series of pulses to pump that information back out of the environment and restore the qubit to its original state.
But notice the cost.
The cost is immense.
This is not natural. Nature doesn't do this for us. We have to isolate the system. We have to cool it down to near absolute 0 to minimize those stray photons.
We have to shield it from magnetic fields, from vibrations, from everything. We are fighting the natural tendency of the droplet to stay a droplet.
This is where that theme of asymmetry really starts to show up. Condensing. That happened automatically. The stray atom just bumped into the qubit.
It's the path of least resistance.
Uncondensing. That requires a team of PhDs, millions of dollars of equipment, and absolute precision.
Exactly. Neymotin calls this engineering its reversal. It's possible, but it requires distinct, focused effort. It's the difference between breaking an egg and putting an egg back together.
I like that.
If you have all the pieces and a lot of glue and infinite patience, you might be able to reconstruct the shell. But breaking it just took a second. It just fell off the counter.
And in the quantum case, putting the egg back together means using external energy to pump the information out of the system.
Yes, you are actively cooling the system to remove the entropy, the disorder that was created when the information leaked. You are paying an energy tax to erase the record.
So this is possible, but it's an uphill battle. A very expensive, very difficult uphill battle against nature.
A battle we are only just learning how to fight, and only inside very, very small boxes.
Okay, so that's the lab. That's the controlled environment. Now we have to talk about the real world. Regime 3, the effectively impossible.
This is where you and I live. This is the regime where the world knows.
The record has escaped. The record radius has exploded.
The information is everywhere. Let's go back to the steam analogy. Imagine you boil a kettle of water, the steam shoots out. But this time, the window is open.
Uh-oh.
The wind is blowing. The steam disperses out the window, across the street, mixes with the clouds above the city. It's now part of the global weather system.
And now someone tells you, put that specific droplet back together.
Right. Not just any water. You have to reconstruct that specific droplet that was on your window. To do that, you would need to track down every single molecule of water vapor that left your kettle.
You'd have to find them miles away, distinguish them from the trillions of other water molecules in the air.
And force them all back into the kettle at the exact same moment, reversing their trajectories perfectly.
Which is, it's not just hard, it's impossible.
It's physically attainable in terms of the laws of physics. No law says you can't catch a molecule, but it is effectively impossible because you cannot control an environment that large. The information required to do it is astronomical.
And this is where Nemotin brings up Schrodinger's cat. And I love this because he doesn't get into the whole is it dead or alive paradox. He
Yeah.
avoids the philosophical trap.
He does. He looks at the cat as a physical object, a macroscopic system.
He calls the cat a factory for environmental records.
That is such a cool phrase, isn't it? A factory for records.
It really paints a picture.
Think about it. A cat is big, it's warm, it's breathing. It is constantly radiating heat. That's a flood of infrared photons carrying information about its temperature and shape, flying off in all directions at the speed of light.
Okay, so there's one record, heat.
It's constantly displacing air molecules. The very act of being there pushes the air around it. Those molecules bounce off it and carry away information about its position.
Record number 2, air.
It's purring, maybe. That's a sound wave, a vibration traveling through the air and the box. It has a gravitational field, however tiny, that is different if it's lying down versus standing up. Every fraction of a second, the cat is broadcasting its state to the universe. I am here, I am warm, I am alive. Or, I am here, I am cold, I am not.
So even if you put the cat in a perfectly sealed, opaque box,
The box gets warm. The outside of the box will be a fraction of a degree warmer if the cat is alive. The box vibrates with the cat's heartbeat. The information leaks
it's hemorrhaging information.
constantly. To uncondense the cat, to turn it back into a superposition of dead and alive, you would have to catch every single photon that left the cat's body.
Not just the ones inside the box, but the ones that warmed the box and then radiated away from it.
Exactly. You'd have to catch every air molecule the cat breathed out and reverse its path. You'd have to undo the vibrations in the floor. You'd have to erase the memory of the cat from the entire universe.
And that is why we can't walk through walls.
That's it.
That is why the past is solid. Not because the math forbids it, but because the record is too broad. The record radius for a person or a cat or a coffee cup is effectively infinite.
It's a scale problem. It is the ultimate scale problem.
This really clarifies the so what for me.
Yeah.
We often hear about quantum weirdness and wonder, why doesn't this happen to me? Why can't I be in two places at once? And the answer is, because you are leaking information like a sieve.
You are a condensation machine. You are constantly solidifying your own reality and the reality of everything around you just by existing. You create a record that is instantly too complex to erase.
So we've got the loop. Vapor to droplet is easy. It's downhill.
It's a natural flow.
Droplet to vapor is possible, but it gets exponentially harder the longer you wait and the more the information spreads. It's a steep uphill climb.
Correct. From a gentle stroll in a lab to an infinitely high cliff in the real world.
This brings us to the final section of the paper, and this is where the philosophy meets the physics. We have to talk about time.
Time, memory, and thermodynamics.
Because if the math works both ways, if uncondensation is technically allowed by the laws of motion, why does time only go forward? Why do we remember the past, but not the future?
This is one of the deepest questions in physics, and Nemotin connects it directly to this condensation loop. He argues that the arrow of time is not some fundamental property of the universe.
It's not a built-in feature.
No.
Yeah.
He argues it's actually just a result of the universe preferring to spread records rather than erase them. It's an emergent property of information.
Let's break that down. Connect it to entropy for me.
Okay. In thermodynamics, we usually talk about entropy as disorder. A messy room has high entropy. But a better way to think about it, a more modern way, is information spreading. Think about coffee and cream.
The classic example. You pour the cream in, it swirls, and eventually it mixes completely. You have light brown coffee.
Right. That is condensation in this analogy. The information of the cream, its whiteness, its position, has spread throughout the coffee. It has created a record in every part of the liquid. It's easy to do. You just stir or even just wait. It happens naturally.
And uncondensation.
Uncondensation is trying to unmix the coffee. It is trying to get all the white cream molecules back into the spoon and leave the black coffee behind.
Which you can't do. It's impossible.
Well, it's not strictly impossible. You could do it if you had microscopic tweezers and could see every molecule and you had eons to pick them out one by one. But it fights against the natural statistical flow. It requires a massive amount of energy and information to pull off.
So condensation becoming a fact, making a record, aligns with the universe's natural tendency to spread things out.
Exactly. Condensation equals spreading information. That's high entropy. Uncondensation equals concentrating information. That's fighting entropy. The universe hates concentrating information. It wants to share. It wants to broadcast.
So the arrow of time isn't this magical clock ticking on the wall of the cosmos.
No.
It's just the feeling we get because it's so much easier to make a record than to destroy one.
That's it. Time feels like it moves forward because records accumulate. We accumulate memories in our brains. The environment accumulates scratches, heat, dents, fossils. The past is just the collection of all these condensed records.
And the future is the realm of uncondensed vapor, full of possibility.
Precisely. To go backward to reverse time would mean erasing all of those records. And since the universe resists erasure on a massive scale, time pushes forward, accumulating more and more records as it goes.
That is profound. It really reframes the whole idea of the universe remembers.
It does. We used to think of an observer as a person with a lab coat, or even consciousness itself. But in this framework, the universe itself is the observer. The environment is constantly observing itself, recording itself simply by existing.
And that's why reality feels stable. That's why my coffee cup stays on the table.
Yes. Classical reality feels stable because the environment is constantly reinforcing that record. Every photon bouncing off it, every air molecule is constantly saying, the cup is here, the cup is here, the cup is still here. If the environment stopped watching, the cup might dissolve back into a vapor of possibilities, but the environment never blinks.
It reminds me of what we said in the last episode about removing the mystical observer.
Right. QC quantum condensation removed the mystical observer and replaced it with a physical process. Record creation.
And QUC.
QC quantum uncondensation removes the mystical collapse.
Oh, so?
Well, historically, people thought collapse was this sudden, magical, irreversible snap, a break in the laws of physics. But if the switch is just record creation, then reversing it is just record erasure.
It becomes a physical process.
It becomes a physical process. It's difficult, it's expensive, it's rare, but it's physical. It's not magic, it's just thermodynamics.
So let's look at the asymmetric loop one last time. We have leg 1. Possibility to fact.
Fast, easy, automatic, driven by nature. That's the vapor becoming the droplet.
And leg 2. Fact to possibility.
Slow, hard, expensive, resists nature. That's the droplet trying to turn back to vapor.
And this asymmetry is why the world looks the way it does. We live in the condensed phase because it's the stable phase. It's the bottom of the hill.
We are the droplets that stuck.
I love that. We are the droplets that stuck.
It's true. We are the records that the universe managed to preserve long enough for complexity to arise.
You know, when we started this journey with the first paper, I was thinking about quantum mechanics as this alien thing, something that happens in a lab with lasers and mirrors.
A world apart.
Yeah. But this framework condensation and uncondensation makes it feel surprisingly familiar. It feels like weather. It feels like thermodynamics.
That's the power of a good analogy. And Nomoten's goal here was to bridge that gap, to show that the weirdness of the quantum world isn't separate from our world. Our world is just what happens when the weirdness gets recorded on a massive scale.
It's a solidified version of the weirdness.
Exactly. It's the fossil of the quantum wave.
So we've traveled from the vapor, watched it condense into a droplet, asked if it could evaporate, and realized that yes, it can, but you have to fight the entire universe to do it.
You have to fight the memory of the universe.
Which brings us to the end of our deep dive. We've closed the loop, we've seen the mechanism, and I think it leaves us with a very different view of reality. It's not just stuff, it's information, it's memory.
It is. And that persistence, that difficulty of erasure is what allows us to exist. If uncondensation were easy, if records dissolved as easily as they form,
we wouldn't be here. The universe would have no memory.
History wouldn't exist. There would be no cause and effect. We would just be a soup of fluctuating possibilities, a constant fizz with nothing ever taking hold. The difficulty of uncondensation is what gives us a past.
That is a beautiful thought to end on. We usually complain that we can't change the past. But maybe we should be thankful that the past stays put.
I think so. Its stability is what makes us possible.
This has been a fascinating two-part journey. I hope it gave you, the listener, a new way to visualize the invisible machinery running the world. It's not magic, it's physics, but it's physics that remembers.
The universe remembers, and reality stays definite because of that memory.